All right. So let's pick up where we left off. And here are three vectors. These are all in R3, right? Because we've got an x coordinate, a y coordinate, and a z coordinate, right? So they're in R3. And so the first question we want to explore is, are they independent? Okay. Are these independent? Are these independent? And we talked about how to do that. Basically, when we want to just as a reminder, we want to solve c sub 1 times v sub 1 plus c sub 2 v sub 2 plus c sub 3 v sub 3 equals 0. Okay. Now let's mention here, this right here we're going to refer to as a linear combination of vectors. Okay, we're going to use that term throughout this section. A linear combination of vectors is just the sum of vectors with some scalar multipliers or coefficients, right? So 3 times v sub 1 minus 7 times v sub 2 plus 2 times v sub 3 is a linear combination of those three vectors. Change the different coefficients and you've got a different linear combination. But continuing on, if I want to solve this, right, I'll put in all the details here, but eventually we'll just kind of go right to the end and I'll tell you where that is. What we're trying to do is here's the equation kind of in expanded form. And of course that leads to this system. Which leads to this augmented matrix. Okay, and now we need to reduce that. We need to find the RREF of that matrix. Okay, and so I threw that in my calculator, and there's the RREF. And you'll notice we have each column has a leading term, so we have no free variables. So this has a solution, a single solution, and in fact we can read the solution right off, right? Because if I translate these rows, each of these rows, this is back into equations. This is 1c1 equals 0, 1c2 equals 0, 1c3 equals 0, and there's my single solution, 0, 0, 0, right? And so of course the interpretation of that is, if you just get the solution 0, 0, 0, then that means they are independent, right? Okay, if you just have a single solution, or put another way, if the row reduced echelon form is the identity matrix with a column of zeros, right? You just get you have independence. Now, so let's talk about the absolute shortcut way to answer this question that doesn't require you to write all of this, although I think it's very important to understand all of this middle stuff so you can understand the shortcut. The shortcut is simply this: take your vectors that you're testing for independence and create a matrix out of them. Actually, I'm going to write it this way. Create a matrix out of them like that. You don't even need this column right there. So you just create that 3 by 3 matrix with all your vectors, put your vectors in a matrix and reduce it. If that matrix reduces to the identity matrix, they are independent. If it reduces to anything else, then they are not independent. Okay, they are dependent, and you can use that to find ways to write one of them in terms of the other two. But so that's the shortcut. Anybody comes up to you on the street and says, are these vectors independent? Just throw them into the matrix, reduce the matrix, and see if it's the identity matrix. If it's anything other than the identity matrix, then they are dependent. Okay? Okay, so here's the interesting idea. We are in R3, as we said earlier, and we have 3 vectors. Okay? So I say that purposely because if I were in R4 and had 4 vectors, I would have the same discussion. But here's the idea you need to understand. 3 independent vectors, such as these, in R3 form what is called a basis of R3 because of 2 things. There are 3 of them in R3 and they are independent. Now, what does that mean? What does it mean to be a basis? That means if you give me any other vector in R3, I can find a linear combination of v1, v2, and v3 that equals that vector. Okay, let me show you what I mean here. All right, so I'm just going to pull one out of thin air. Given W equals, we'll just go 1, 0, 3. Write W as a linear combination of V1, V2, and V3. All right. Okay. So what we're saying there is I need to find a C1 times V1 plus a C2 times V2 plus a C3 times V3. So I'm taking a little bit of V1, a little bit of V2, a little bit of V3, adding those together, and I want to end up with W. Okay. I want to solve that equation. I want to figure out what the C's are. How much do I need to multiply by V1? How much do I need to multiply V2? How much do I need to multiply V3 so that I can add them together and get this? Now, if I were to fill in all the blanks, it would look like this, right? To find this linear combination. So you can imagine what that would look like. Basically, it will end up with this matrix, right? 1, 2, 1, minus 4, minus 1, 2, 2, 5, 3. Oh, that's a shame. Let's try that again. 1, 2, 1, minus 4, minus 1, 2, 2, 5, 3, 1, 0, 3. And so in order to solve this equation, this equation, I need to solve this system, and I need to reduce this matrix. So we'll throw that into our calculator to find the RREF of this guy. All right, we've done that. There's our RREF. And so if I convert that back to equations, right, it's going to be C1 equals that, C2 equals that, C3 equals that. Okay, I have a single solution. That means if I take negative 67 times that vector minus 4 times that vector plus 26 times that vector, I get this vector. All right. The way I think about this is I have just used these 3 vectors to build this vector. Okay. And this is how much I use of each of those. All right. So here is what's fascinating about this. Because these vectors are independent in R3, and there are 3 of them, and they form a basis for R3. You give me any single vector in R3, and I can build that vector using V1, V2, V3. Or, to put more precisely, I can express that vector as a linear combination of my 3 basis vectors. Okay, so these are all I need to describe R3. Okay, they're sufficient to get me anywhere I need in three-dimensional space. All right, so if I want to get to the point one, or the place 103, I can just take negative 67 of V1, negative 4 of V2, and 26 of V3, and boom, I end up there. All right, I can get to any place using these three vectors. That's what it means to be a basis for a space. All right, for a vector space. Now, if it's R4, then we would need 4 independent vectors to be able to have a basis. Okay, to have a basis. Now, these aren't the simplest. There are lots of bases for R3. All right, the simplest base is this. It would be something like this, right? 1, 0, 0, 0, 1, 0, and 0, 0, 0. So it's real easy to see that those are independent, because if you put them in, you can real easily see that they're independent, because if you put them in the little matrix, like I said, and reduce it, oh wait, it's already reduced. Reduce it, and it already ends up being the identity matrix. It's already the identity matrix. So they are independent. There are 3 of them in R3, so they are independent. So I can build any vector in R3 out of these. What was our vector W? 1, 0, 3, right? How would I build that? Oh, super simple. I don't even have to do any work, right? C1 equals 1, C2 equals 0, C3 equals 3, right? Just check that out. C1 times V1 plus C2 times V2 plus C3 times V3 equals W. Okay, these are the standard unit vectors, right? So those are the ones that are simplest to use. I can obviously get to any place in R3 using those 3 V's. You know, and they form the basis of our three-dimensional graphing system, right? If I want to get to a point, this would be my V1 direction, V2 direction, and V3 direction, right? I could come out this many V1, and you know, however many V2, 3 of those, boom, boom, and then boom, and I can get to any point I want. Okay. But again, so that's the simplest basis. But we could create some crazy axis system based on, you know, these original V's that we played with up here. Okay. All right. So that is the idea of linear combinations and basis. And it's a fascinating idea because it lets us explore, you know, kind of form the building blocks of these R spaces.